Somewhere in the constellation Libra, a star is burning that, by our best measurement, is older than the universe that made it. Not metaphorically, numerically. Its age came back at roughly 14.5 billion years, inside a cosmos clocked at 13.8. The error bars overlap barely. Astronomers gave it a nickname before they gave it an answer: Methuselah. And the question it raises is not whether the star is wrong, but whether the framework we use to weigh it might be. The catalogue entry is HD 2-hundredth, a subgiant drifting 190 light-years from Earth, visible through a modest telescope and almost entirely barren of heavy elements. That barrenness is the first clue. Iron, in stellar chemistry, is a timestamp. Every generation of stars enriches the gas that forms the next. HD 2-23 carries less than 1/200th of the Sun's iron. It was forged when the universe had almost nothing to forge with. In 2000, the Hipparcos satellite placed its age at around 16 billion years. Impossible on its face. A 2013 Hubble parallax refinement brought the figure down to 14.46 billion, give or take 800 million, still older than the cosmos. The math is not exotic. Astronomers measure the star's luminosity, its surface temperature, its precise distance, and run those against stellar evolution models calibrated on thousands of other stars. The models are not new. They are the same ones used to gauge globular clusters, white dwarfs, the Sun itself. And those models, applied to this one subgiant, return a number that breaks the timeline. The error bars are the entire story, and we have not yet earned them. Begin with what changes when you push the assumptions. The star's oxygen to iron ratio matters enormously. A slightly higher oxygen abundance shifts the modeled age downward by nearly 1 billion years. Its helium fraction matters. The treatment of convection inside the stellar interior matters. Every one of these is a knob, and every knob has uncertainty stacked on uncertainty. Some theorists suggest the star may not be a single object at all, but the merged remnant of two ancient stars, which would reset the clock entirely. Others argue the distance measurement, even refined by Hubble, still carries a quiet bias. Each adjustment is defensible. Each one buys a few 100 million years. Stack enough of them, and Methuselah slides comfortably under 13.8 billion. Oh! But notice what the exercise costs. To preserve the standard model of cosmology, we are tuning 4 or 5 independent parameters in the standard model of stellar evolution simultaneously in the same direction. That is not a measurement agreeing with theory. That is a theory being held in place by hand. The story goes that this is normal science. It is also fragile science. Consider the composition more carefully. HD 2-83 sits in what astronomers call population out. The second generation, formed from gas seeded by the first stars that ever burned. Those first stars, population 3, have never been directly observed. They are inferred entirely from what their descendants carry. And HD 2-83 carries the lightest fingerprint of any subgiant within reach. Its lithium is depleted in a pattern consistent with Big Bang nucleosynthesis followed by surface mixing. Its carbon is faint. Its alpha element ratios point to enrichment by a single, very massive supernova rather than the slow accumulation of many. Imagine if this star formed perhaps 200 million years after the Big Bang, in a pocket of gas barely enriched by one dying giant. That timing is physically permissible. It is also tight. It demands that structure formed faster than our cleanest simulations predict, that the first stars lived and died on a schedule the cosmological clock barely tolerates. The age estimate, in other words, is not just a number from a model. It is a number that the chemistry independently corroborates. And that corroboration is what makes the discrepancy refuse to disappear. The honest reading is this: Methuselah is almost certainly not older than the universe. The error bars do overlap. The cosmological age itself carries roughly a 20 million year uncertainty, and Planck's measurement of the Hubble constant remains in open tension with local distance ladders. A tension that, if resolved against Planck, would shave another few 100 million years from the cosmic age and widen the gap again. So the star is not the anomaly. The frameworks are. We have a model of stellar interiors confident to 2 decimal places, and a model of cosmic expansion confident to 2 decimal places, and where they meet, they touch by less than the width of their own uncertainty. That is not consensus. That is a coincidence we have agreed to call consensus. What Methuselah exposes is how thin the floor is beneath stellar evolution. How much of what we call a measured age is a calibrated guess held steady by assumption. Keep that fragility in mind. The next star we examine will not merely strain the models. Its light behaves in a way no natural body is supposed to behave at all. Methuselah is the warning shot, a reminder that our most confident numbers sit on calibrations we rarely interrogate, and that the gap between a star's age and the universe's age can hinge on a single assumption nobody has tested in 50 years. The pattern is larger than one subgiant in Libra. Across the sky, objects keep arriving at the edge of what our models permit. And some of them are not arriving alone. In the next expedition, we follow a star whose brightness drops in patterns no asteroid, no planet, no dust cloud has ever produced. If you want to be there when that one breaks, the subscribe button is how you stay with the series.